Welcome everyone to this meeting of the Compute Accelerator Forum, which this week is joined with our colleagues in Atlas who are having their software and computing meeting at CERN this week. So I don't really have a lot of intro to say other than just to advertise today's meetings. So first of all, we'll hear from Charles about portable parallelization work in HEP CCE. And then after that, similarly on HEP CCE from Peter on high performance IO. So after this meeting, our next meeting before the summer break will be the 12th of July, where we'll hear about the Alice O2 framework. August being summer break, we've cancelled that obviously, and then we'll reconvene in September, where I think we'll have a very interesting presentation from Jonas and others on the RISC-V architecture. There are other meetings listed in the full Indico category listed and linked here. We already have some lined up beyond September, but as ever, if you'd like to present or to present something at the meeting or just to propose a topic you think we should look at and arrange something for, then obviously, as usual, get in touch with us at the organising committee at the address link there. So with that out the way, I'll hand over to Charles, who'll tell us about HEP CCE portable parallelization.
Great, thank you, Ben.
Okay. So, well, Charles, before you do anything else, please bring the Zoom window over here. Then I can start the screen sharing. Just so that. Then you could go out of full screen because just double click the thing. Yep. And while you bring that up to full screen, if anybody who was here in the previous meeting lost a power brick, well, come see us afterwards.
Good, Attila, good.
All right. So thank everyone for coming, and also to the HSF Forum for giving us this opportunity to present our results from the past few years. I'm going to go a little bit beyond what we'd initially discussed or planned in the title, which is not just the results from the portable parallelization strategies part of HEP CCE, but really to cover all the work that we've done in the past 3 years, and also what we're planning on doing in the next few as we continue the work in HEP CCE. Oops.
You might need to just click on it because no, just with the mouse.
This thing not working?
Now it will. Now this is the.
All right. Okay. Great. Thank you. All right, so for those of you who aren't familiar with HEP CCE, let me just quickly summarize what it is. HEP CCE is a project which is basically exploring the intersectionality between high energy physics and HPCs. And we're doing so by looking at developing practical solutions to porting hundreds of thousands of kernels to multiple different hardware architectures. And we're doing this by collaborating with the HPC and the network communities to develop data-intensive use cases. And HEP CCE is split into 4 main parts. It has a PPS, the Portable Parallelization Strategies group, which is looking at how we can explore the massive concurrency that we now find in modern HPCs, which are full of GPUs. And to do it in such a way that we can write our code once and have it run on all the different hardware architectures, because we have NVIDIA, we have Intel, we have AMD. In the future, we'll probably have other things. And we don't really want to have to rewrite our code for each different architecture. The second group is the iOS group, and that is basically looking at I/O and storage issues by looking at things like new data models with memcopyable and SOAs, and really looking at understanding the fine-grained I/O by doing a lot of workflow instrumentation. The third group is our event generators group, which is looking to see how we can optimize these tools for HPCs. And finally, we're also looking at complex workflows to understand how we can mesh our workflows with the way things are done on HPCs, and they're very, very dissimilar. And there's really a bit of an impedance mismatch between what we do and what needs to actually be done on HPCs. It's an open collaboration. It has interactions with the HSF, with SIDAC Rapids, with Swift, with Iris HEP. And we are split between 4 US labs, 6 different experiments. We have more than 12 FTEs and something like 35 collaborators. So we're pretty large and diverse groups. And at the end of all this, the end game really is to come back to the experiments. And so we have a lot of ties with the different experiments who are involved, with a lot of developers from the experiments being part of HEP CCE. And we have a lot of cross-pollination between the different experiments so we can really exchange ideas well. So let me start with PPS. And when we spun up CCE about 4 years ago or so, x86 was king still. To a large extent, GPUs were just starting to appear in HPCs. We first started seeing the first set of HPCs with GPUs in it, and this trend has only increased since. Right now, 90% of the performance from a large HPC is coming from GPUs, and back then, we were really scared because we had Intel, AMD, and NVIDIA hardware, and there was no one way really to write code that would run on all these different platforms. And this is what the landscape kind of looked like in 2019, where CUDA obviously only worked back then. It still only does work on NVIDIA GPUs. Cocos was just starting to explore other platforms other than NVIDIA. SYCL was kind of in its infancy. There were multiple different flavors of SYCL. HIP only worked on NVIDIA and AMD. OpenMP target offload really only worked on NVIDIA GPUs. I'm not sure actually about the Alpaca because we weren't even really looking at Alpaca back then. And I suspect though that it really only worked on NVIDIA GPUs. And STD-PAR was just barely coming into effect and working on anything other than CPUs. Now though, it looks very, very different. There's been tremendous development in hardware and software. Most of these different sort of portability layers will be able to target in some way or another all the different sorts of hardware that's available. Cocos, SYCL, Alpaca, OpenMP, and HIP, they can all to some extent or another really target every type of GPU that we have available right now. And a lot of them are actually being able to target FPGAs to one extent or the other. I mean, there's really, frankly, there's different levels of green here, so I shouldn't really make them all the same. But we have seen a lot of progress to be able to cover the entire field. So what we have done in the PPS group is we took a bunch of test beds from different experiments, which kind of represented some very typical use cases. And we tried porting them to each of these different portability layers, such as Cocos, SYCL, OpenMP, Alpaca, and STD-PAR. And we evaluated our porting experience by a number of different metrics to see, what it was like to do it. And these are some of the metrics that we came up with. There's a lot of different things, and some are very objective, and some are very subjective. Things like, ease of learning. How hard is it to port code from CPU to a GPU, and then between different APIs for GPUs? What do you have to do with your code to make it run on some of these different APIs? Would you have to give up control of main? Do you have to, what kind of threading or execution model are there? What do you have to do with your EDM? What do you have to do with your build system? What kind of mapping is there with the hardware? Are these platforms going to be around for a long time? I'm sure that, CUDA is going to be around for a very long time. Is Alpaca? What features of the hardware do they support? Can it do atomics? Will it do scans? Things like that. What about interoperability with various types of external libraries, such as TBB or root or various C++ standards? How well does it match onto a big experiment versus a small experiment? A big experiment like CMS or Atlas has lots of developers and lots of people who can port a lot of code if it's hard. If you have a very small experiment, then you'd really have a lot of different sorts of requirements that are involved in choosing some of these layers. What kind of backwards and forwards portability is there going to be with these? You know, are suddenly everything that you've been working on for the past few years not going to be working because the portability layer has said, right, you know, we are changing how everything is being done, and our API is no longer going to be backwards compatible or forwards compatible. You know, what stability is there? You know, how long does it take to compile your entire build? Atlas already takes a very large number of hours to compile a release. If all of a sudden that increases by an order of magnitude, that could be very significant. And then, you know, there's things like, you know, how fast does it run? Which, you know, in some ways is a very important metric, but is by no means the most important metric. And how is it to debug? A lot of these things use a lot of template libraries, for instance, and they can make debugging when you're trying to look at the name of a function, you know, very, very challenging. And then there's things like aesthetics. You know, what does it look like? I mean, some people like the way that OpenMP looks, and some people really hate it. So, you know, there's a lot of different things that you can use to evaluate these platforms. So the 4 test beds that we used are FastCalOSim from Atlas, which is the parametrized liquid argon calorimeter simulation. It's relatively small. It's got, you know, 3 main kernels, which is like a large workspace reinitialization, the main simulation, which is a lot of math, and then a little bit of stream compaction, and there's a little bit of data movement back to the host. It's using 1D and 2D jagged arrays. You know, it's very self-contained. You know, it doesn't have a lot of external requirements. From CMS, we took PataTrack, which is the pixel detector reconstruction. It is considerably more complex than FastCalOSim. It has about 40 different kernels of various lengths. Most of them are very short, so we can use it as a test for things like latency. But it's also doing a lot of more complicated things with concurrency and the synchronous execution and the memory pools. Then there's the WireCell toolkit, which is from June, which it does the liquid argon TPC signal simulation. It has 3 kernels that have a rasterization step, a scatter add step, and then an FFT convolution. So this allows us to explore some of the external libraries like FFTs. And finally, we have P2R, which is also from CMS, which is doing the propagate to R track reconstruction in a single kernel. So I'm going to go through our experiences with the different portability layers. And, you know, I'm not going to really show any numbers in the end of how fast things work, because, like I said, first of all, it would take too long. But also, in the end, the numbers aren't as important as some of these other things are. So for those who aren't familiar with Cocos, well, you know, if I had another hour, I would go in more detail through all these different languages and how they differ or similar to CUDA and other things. But Cocos is a little bit of a higher level of abstraction than CUDA because, you know, well, it tries to target a bunch of different platforms underneath it. So it really tries to separate itself from the hardware a little bit more. It does have these requirements for explicit initialization and finalization, which means that you have to be able to get into your main program, which can be a challenge at times. It has a separate compilation of its library for different backends and for different features. What this means is that you can choose one like serial version, a host parallel version, and a device parallel version. And you have to be very specific as to what you choose. For instance, if you are going to run on an NVIDIA GPU, you have to choose pretty much the flavor of the NVIDIA GPU. You have to say, right, I'm going to be running on an A100 or I'm going to be running on a V100. And if you compile for the V100, it's not going to run on the A100. So this has some very significant impacts on code distribution, because then you have to figure out if you're distributing your binary to the grid, you have to build either locally all the different ones or make sure that at your final destination, you can actually build the right backend. One of the nice things with Cocos is that you can mix and match native and Cocos versions in the same application. So let's say that you have some CUDA code that you are translating into Cocos. Well, you can actually say, right, I'm only going to translate one kernel at a time, and I'm going to have this version that's in CUDA and this version with this Cocos with the CUDA backend, and it will mix and match. So this really helps with the translation process, because you can do it very stepwise. We found that it had very good performance for simple and very long-running kernels, which hide some of the overheads that you get from initialization of data structures and from certain kernel launch latencies that code adds to what you would see on top of CUDA. Some of the downsides are that there's like no good native support of jagged arrays. So you basically have to do things like flatten or pad your arrays if you have jagged arrays. It doesn't really support concurrent kernels other than if you use CUDA backend and only using very specific CUDA features. And concurrent calls to the serial backend are safe, but they're very, very inefficient at this point. We've seen some significant progress over the past even just a year in this respect. Like last year, it wouldn't work at all. Now at least it works, but it's slow. Maybe next year it'll work and it'll be fast. So we'll see. There is no common API to vendor optimize FFTs and random number generators. However, they do supply some of their own. So it does provide a significant amount of portability in that sense. But if you're trying to match, say, binary compatibility with existing like cuFFT that you're using somewhere else, then you might have to add your own kind of interface layer to try to get things to work properly. We found there was very poor interoperability with existing concurrency mechanisms and thread pools such as TBB, and this caused a lot of difficulties for PataTrack, for instance. On the other hand, we found that Cocos has incredibly good developer support. They have a Slack channel; they're incredibly responsive. The developers answer your questions very quickly, and they have a lot of tutorials, a lot of recorded tutorials. They're willing to come out to various institutes and give hands-on training as well. So they're 3 thumbs up in that respect. Alpaca in many ways is very similar to Cocos in terms of it's the way that the code is structured and the way the API looks like. It's considerably more verbose than Cocos. The documentation tends to be pretty sparse, and I think that it has much more steep a learning curve than Cocos does. On the other hand, the developer community, even though it's small, is very responsive and very, very helpful. So some of the code modifications that you need to do are you have to either wrap your kernels in callable objects or use lambdas, and it really has a lot of type depth that have to be used. And this can make some of the compiler errors that you get from it really hard to understand because of all the verbiage is in there. For the memory transfers between host and device, you can either use Alpaca buffers, which takes ownership of the allocation, or you can use views, which wrap existing objects, which have already been pre-allocated. Our attempts to use the Alpaca views inside a fast calosim went, I don't know, there's something very strange happened, and it led to some random crashes that we couldn't understand. PataTrack, on the other hand, didn't have these issues, so it could be that we were just doing something wrong. We didn't have time in the end to fully understand it. But wrapping the or taking ownership made things work fine. It works very, very well with CMake, so that was very handy to be able to do. And like with Cocos, you can mix native kernels and libraries in the same application. The performance was basically the same as the native implementation. So if you're running on NVIDIA, it's the same as CUDA. If you're running on AMD, it was the same as HIP. And if you're running on Intel, it was pretty much the same as SYCL. So SYCL, which is being promoted heavily by Intel, has been advertised as kind of like a one solution fits all. You can select your backend at runtime, which is true up to a certain point. The problem is, though, that when you want to target the different backends and different hardwares, in essence, you really need to have a different compiler or a different build of your compiler to actually pick the specific backend. And so you can't say write your code or compile your code once and have it run on every piece of available hardware without a different compilation. So in that sense, it doesn't live up to its expectation, but who knows, maybe in the future we'll be able to do something better there. It has a very nice simplified code design because it's associating data dependencies with kernels. And so what this will do is automatically migrate data to your device without an explicit memory transfer. You can do explicit memory transfers if you need to. And in some cases, it's considerably more performant than the automatic migration, but you don't need to. There is no concurrence. Currently, there is no support for concurrent kernels with any backend. Now, this is not something which Attila is looking at me funny. I have not been able to make it work.
It is concurrent on NVIDIA backend. If you don't do anything, it runs concurrent kernels.
I have not been able to make that work. Maybe this is a newer version, but
it works.
Really? Okay. So up until I haven't tried this in about 6 months, but the last time I did, it basically serialized all the executions. This is when you have multiple different threads which are trying to use the same, or either the same or different queues. It wasn't working, but this is actually very good to know. This is with one API or with LLVM, or both?
Both.
Okay, I'll have to look into that. But that's very good to know. On Intel hardware, though, Intel has said that they will not support it.
Oh.
Yeah, at least not with their current hardware. So there's both a software and a hardware limitation there. But maybe that as well will change. It has excellent interoperability with existing concurrency layers such as TBB, OpenMP, and MPI. So that worked out very nicely. And has pretty much seamless integration with the various build layers. And we also saw very good performance compared to native, with CUDA or HEP. And since it is being strongly supported by Intel, there's a lot of good developer support behind it, and they're very proactive with responding to these bugs. OpenMP target offload was the one which really had the greatest difference of opinions of how people found their porting experience. Some people thought it was really easy and very trivial, and some people thought it was incredibly challenging, and they thought that OpenMP hurt your eyes to look at. There was significant variation between the performance characteristics of different compilers, from using GCC versus Clang versus something else, different compiler options, different tuning options. It was much more challenging to make it actually work well, with a significant amount of performance. There was a lot of, there were some operations that were unsupported, such as scan and memset, and some that are horribly less performant than native ones on CUDA, such as atomics. That has been, the atomics one specifically has been improving, but it's still a lot worse than CUDA. The documentation tends to be pretty sparse, especially for some of the more advanced features. And debugging and profiling is very challenging because of the extra OpenMP code infrastructure that gets added on top of it, and for the architecture-specific plugins that are loaded at initialization. So it's definitely probably the most challenging one to actually debug. And the last one is stdpar, which is very much of a different beast than the previous ones. It's not meant to be a direct replacement for a low-level language like CUDA. It's pure C++. It basically was introduced, quite a while ago with C++17. It was really meant to be able to do parallel execution of STL algorithms on CPUs. But over the past few years, NVIDIA and Intel have added or have created compilers which can target GPUs. But still at a fairly high level. There you have no low-level controls. You can't set your launch parameters of a kernel. You can't do synchronization, and they really aren't intending it to be a direct replacement to CUDA, but rather a stepping stone between very serial type of programming and something like CUDA. It will give you an easy pathway onto GPU programming without having to do a lot of modifications to your code. Right now, there's support for NVIDIA GPUs using NVC++, and Intel GPUs using OneAPI DPL. And also you can target multi-core CPUs with NVC++ and G++, and probably, I haven't tried it though with OneAPI DPL. The one that I've used the most is NVC++. And it's still rather immature compared to, say, GCC. There are still bugs. It can't compile root all the way through yet, though they're working on it. And they see this, basically compiling root, they being NVIDIA, see compiling root as a benchmark of their performance. And they want to have that available when they release Grace Hopper, or basically when they release Grace. So they see that as a very imminent deadline, because they see us being the HEP community as being a very important customer, and they want to make sure that we can use Grace and their ARM platforms for our workloads. Some of the issues that this engendered were that we had to have this Frankenstein build system where we had to compile some part of the code with G++, another part of the code with NVC++. And this caused both build issues, and also, since it's using basically shared memory to offload to the GPU, you don't do direct memory transfers. What it does is page faults. So when you access a page of memory on the GPU, it knows to transfer it to the GPU from the CPU. But in order for that to happen, it has to have instrumented that piece of code. It has to have allocated that code with NVC++. So that means that if you compiled, if you have a piece of memory that you say compiled with GCC in one part of your code, and then you want to offload it with another piece of your code that's compiled with NVC++, you actually have to copy the memory and reallocate it with NVC++ before you can offload it. Now, ultimately, this is probably not terribly significant, because we can't compile everything with NVC++ now, but when we can compile everything with NVC++, then all this will go away. The compilation at this point was still a lot slower than G++, which is obviously going to be an issue for some of the big builds. And also we saw some really unusual memory transfer speeds between AMD CPUs and NVIDIA GPUs, which we didn't see with Intel CPUs, where we saw performance that was 10 to 50 times worse for certain really pathological cases. In terms of overall performance of kernels, we actually saw some remarkably good performance. In fact, some of the kernels ran faster with NVC++ and STD-PAR than they did with the original CUDA versions. So basically what NVC++ does is it uses thrust to do the implementation on the GPUs. So if your kernel really maps well onto something that thrust does, or is a thrust concept, then you should get very good performance. But we also saw some kind of much worse performance, especially with very small kernels, which have a much higher latency. I think that NVC++ really offers us, or STD-PAR offers us, a path forward to C++ standardization, which maybe will avoid a lot of the issues that we see with some of the other things like Cocos and Alpaca and Sickle. And maybe with C++26, with STD exec and schedulers and senders receiver, we'll actually start to see some more GPU low-level features that will allow us to program closer to the hardware, shall we say, in a more efficient way. So let me just summarize with some of the recommendations from PPS. The software and the hardware are still very rapidly changing. We've seen tremendous development over the past few years. We've had a lot of interactions with the developers of the various APIs, with hackathons and to fix bugs, and our experiences have affected or have influenced their code, which I think has been very, very positive. And in many respects, some of these results really remain preliminary because the hardware and the software really continues to change. The API recommendations we find are very application dependent. In the end, they all perform approximately equal for simple kernels or very long-lived kernels. But complex algorithms and chain kernels bring out the weaknesses of really kind of all the APIs. The interaction with external libraries adds a lot of extra complexities. So you really have to be careful in choosing your portability layer if you have various types of external libraries. And sometimes even compilation with these things can be an issue. The learning curve or the language complexity of the APIs is really not all the same. And STD-PAR is probably the easiest and OpenMP may be the hardest, but also OpenMP is in the middle, depending on what you want to do with it. All of this is very subjective again, but maybe STD-PAR, simple OpenMP, then Cocos and SYCL, or in between, and Alpaca is yet another step up, and then OpenMP if you really want to get into the really nitty-gritty and understanding what it's doing and eking out the last bits of performance. I mean, that's probably kind of like what the range is. But like I said, it's very subjective and it's depending on code complexity, and also on previous experience with OpenMP. Not surprisingly, the person who thought that OpenMP was a breeze for porting our kernels had 5 years of experience with OpenMP in general. So, it's kind of the same for any language. When you start with porting from serial code to GPUs, a lot of times it's really that first step, which is the hard part. It's not necessarily doing it to Cocos or doing it to SYCL, but it's changing the concepts. How are you going to restructure your algorithms to expose the concurrency? What are you going to do with your data structure so that it's offload or GPU friendly? Once you have that nailed down, in the end, choosing one of these languages is not particularly onerous. It's really doing that initial step of making it very, parallel friendly. On the other hand, if you're starting with code which has already been heavily optimized for CPUs, such as some of the event generator stuff, for instance, where they really tweak performance for x86 with wide registers or things like that, a lot of times you have to de-optimize everything to get it back to your basics before you can actually make it run on GPUs. At this point, it's still fairly challenging to extrapolate to the next 5 years and beyond. I think that we are actually moving towards standards. Certainly the various vendors are pushing towards standards. Unfortunately, they're kind of pushing in different directions. NVIDIA is pushing in one direction and Intel is pushing in another one. NVIDIA kind of wants STD-PAR and it wants things that look a lot like Cocos, whereas Intel wants, SYCL. But within the next, 5 or so years, I think that there will be some kind of meeting in the middle. Another thing which I think is going to be very interesting to monitor is that we are seeing the increasing proximity of CPUs and GPUs and memories. And I think that the Grace Hopper platform is going to be a litmus test. And depending on how our code works on that, I think that we might really change how we decide what to offload, because with this really close proximity of CPU and GPU with very fast memory, we might start, instead of just offloading big chunks of code, we might say, oh, look, we can just offload these 10 lines. And because the memory is so fast and the interconnects are so wide, we really don't have to worry about latency the way we have had to in the past.
Should we possibly ask questions about this first part now, or should we do it at the beginning?
Yeah, why don't we pause now? Oops. And see if anybody wants to ask questions about this before I move on to the summary of some of the other event generators and other stuff.
I should monitor what's happening on Zoom, but
I don't see any hands raised.
So, hi, Oksana here. I was wondering, because many of those issues are not unique to high-end physics, right? So there are plenty of other communities who probably also are facing the same. So how is the interaction going on within HEP CCE or otherwise with other
it's
users?
interesting. When I went to a PASC conference, when was it, in 2020, and we first started looking at these things, a lot of people were complaining that they were facing the same issues of, portability layers. How do we make it work on the different platforms? And the reactions from the vendors at this point were, "Oh, that's your problem." Right? And when we started working with Intel on A21, so Aurora, basically, and they were advertising SYCL as being the end all and be all for programming on Aurora. They said, we will not support anything other than Intel hardware, period, right? But that was from fairly high up in the management. And the engineers inside of Intel were saying, no, that's not going to fly. And we saw a lot of progress pushing from within Intel as well as from the developer, the user community to change that. And we saw Intel buy CodePlay to be able to target NVIDIA hardware. And we saw a lot of interactions with different communities, with the LLVM build, which can now target AMD hardware as well. They went from treating HEP CCE, which was back then the only way of targeting AMD, as basically, oh, this is somebody else's work, we're not really interested in it. And now they're actually very strong supporters of, well, it's now called OpenSickle. Though that actually may change as well, from what I understand. But so there has been a lot of community pushback against having a lot of isolated software solutions, and I think this has been very good that we are seeing convergence, and which is also great because the DOE funding agencies back then were also not interested in really doing anything. I remember when Frontier first started up, and we were saying, how can we run on Frontier? And they said, oh, well, you'll just have to use HIP, but then I can't use that on Aurora. They said, oh, well, that's your problem. So things are changing, at least.
So on this last point, and this is kind of becoming a clearer and clearer trend, right? Does this sort of indicate that we shouldn't necessarily do huge amounts of work before it's a bit clearer in the next few years what the direction of the manufacturers is going?
So I think we should do huge amounts of work to port to GPUs.
Yes.
I think that understanding how our code gets parallelized is very important. I don't think the explicit choice at this point, in the next year or 2 years of a language is as important. I don't think that we have to choose Cocos right now. I think that it makes a lot of sense to invest a lot of effort and say use CUDA right now, and it will get us 90% of the way.
The CPU, GPU memory.
Yes, that's what I was talking
yes.
about. Yes.
No, but going beyond that, because CPU, GPU memory, you still need to parallelize your code well to be able to use a GPU efficiently. But I think they will offer us a lot more avenues of how much code we can offer. Instead of having, when we have to sometimes worry these days, oh, we're doing so much transfers between little kernels, host to device back to host, back and forth. And should we change that? Should we now change that so that everything gets done and stays on the device all at once? Is that going to be as much of an issue in 2 years? Maybe, maybe not. It'll always be some of an issue, but I think that level will probably go down. Then again, Grace Hopper is not cheap. It's not going to be on your desktop.
No.
Right.
I mean, there's also the point which many people have made that this work that you're talking about often leads to more efficient CPU code as well. Yeah. So
actually, that was one of the very interesting things that we found with std_par. So for fastcalosyn, we had the code which was originally written in C++ for CPU. It was translated into CUDA code. And then from CUDA code, it was ported to Coco, Sickle, Alpaca, and std_par. And std_par allows you to run single-threaded on a CPU. And when we compare the multiply translated code with std_par running on a single thread on a CPU, it was about 30% faster than the original CPU code.
Curious.
So exactly.
So Charles was expressing it very, very well, that I myself would not hope all these memory developments to be the silver bullet. So a lot of people got very excited about what Apple is doing because they are doing a little bit of a different thing than what NVIDIA, AMD, and Intel are doing. So if you look at what Grace Hopper is doing, they don't just have a single memory area like the M1 and M2 chips do. There are still memory areas that are a lot closer to a GPU or the CPU. The bandwidth is very good between these, and the GPU can access the CPU memory fairly fast and vice versa. But if you want ultimate performance, you still have to worry about memory. Now, yeah, maybe they will change. Maybe in a future version of Grace Hopper, there will only be a single type of high bandwidth memory, and all the devices are just talking to that. How expensive that might become, I have no clue. So, yeah, difficult question.
So I want to go to your second to last bullet. You know, two standards mean you don't have a standard, right? And so do you think this is a Sony Betamax situation and there'll be one winner and one loser? Or do you think, I mean, do you think the committees, like the C++ committee that want a standard, have enough power to, I don't know, get the vendors to cooperate?
Well, I'm hoping that it won't be decided by the adult film industry like it was with Sony Betamax.
That's just a rumor that that's the strongest.
I think that it's going to be, you know, a meeting in the middle. I think the standards committee is going to be very influenced by what we ask of them. You know, senders and receivers, yes, as high energy physics and also outside of high energy physics. And I think it really it behooves us to develop test cases. And this is actually some of the things I want to talk about for the future of CCE. To say, right, these are what our requirements are. These are some examples. Help us make it better, you know?
At the same time, I don't think we'll ever end up with a single language. So some of these, for instance, OpenMP, unless something very unforeseen happens, OpenMP will continue existing because it also has a lot of other areas.
Just like Fortran has always been around, OpenMP will as well.
Yes. So, but yeah, it's not impossible that if what the C++ committee tries to make this STD-exec or whatever they are calling it these days, if that ends up being everything that they hope it will be, yeah, maybe CUDA, HEP, and even SQL might go away eventually.
Yeah, I suspect we will never lose CUDA because no matter how good a standard you make, it will never be able to get to the hardware the way something that is written specifically for the hardware can. So there will always be people who want to use the lowest level language possible, you know, whether it's assembler or CUDA or whatever.
But didn't you find that one of the portability layers did better than CUDA?
Yes, that was, you know, for a specific application. It's not going to be for all of them.
But then, I mean, you're saying that you'll never get rid of CUDA because it's always going to do better in performance. It's built for that hardware, but yet it's not always, you know.
It's, you know, you can always find cases where it does well and where it does very poorly. And, you know, we happen to have one algorithm that managed to translate into a thrust kernel very nicely. And so it ran very fast. We had other, I mean, and it wasn't just the kernel, it was also the amount of data that we were pushing through it. When we took the same kernel and we had it, you know, this is from fastcallicin, and we had it at a different energy, it didn't perform nearly as well, for instance. Or if we were ganging data between multiple events, you know, it didn't perform as well. So it's, you know, we can find a use, or we can find a specific case where, look, it performs so much better, but that's not always going to be the case. And there's some people who are going to be, you know, you're writing something for your trigger, for instance, and you are limited by a certain amount of, you know, microseconds before the next bunch crossing comes or whatever it is. And you want to be able to tune it very well. So it could very well be that you'll want to run a certain part of your code with CUDA. Now, a lot of these languages will allow you to mix and match. So it might be you only write one specific thing in your entire chain with CUDA and the rest with a more standards-based library or a more portable layer.
At the same time, I hope for a future where we will be dealing with all of these optimizations in the same way in which we try to make use of AVX and all of these instructions in our host code at the moment, where in very specific parts where all of these hardware level helps in our code are significant, there we will put some pre-compiler macros or whatever we use at that point. But other than that, we write some standard code. Maybe that will be possible in the future, that we'll just write NVIDIA specific parts where that's really needed, and everywhere else, just generic C++ code.
Well, one question you might get from the other room, Charles: should I take your fastcalc import and run it on the grid for my production jobs, or should I wait until you go somewhere?
You can run it right now. I mean, not my fastcalc because right now ours is a standalone. It was branched from Atlas 5 years ago. But there is fastcalc inside of Athena right now, which you could do that as long as you have, right? I mean, it's using the CUDA version. So it isn't using any of these portability layers. But you could run that on the grid.
Right, but the Atlas simulation group will have its own very strong opinions about this. So let's maybe discuss this there.
Just saying you could.
I mean, I was wondering about in case this direction into standard PAR or the future iteration of that wins. I mean, that would kind of mean, at least as far as I see, that one is locked into the compiler from the vendor, also for the code which not explicitly targets the GPU. Wouldn't that kind of be a problem? I mean,
I don't see why you would be locked into a vendor compiler. I mean, GCC, for instance, will support a standard, won't it? And that's not
but as, the output is not necessarily binary compatible, isn't it?
I don't know, but as long as it's standard C++ and
it's not the ARM standardized, as far as I know.
yeah, but that will always be the case. When you write C++ right now, when we build it for ARM, that's a different binary than when we build it for x86.
Yeah, but for ARM, for example, you have multiple vendors which provide compilers for CPUs, but it's presumably never going to be the case that there will be multiple compilers which directly target GPUs because they don't get the low-level information to do that.
So right now, what's happening is that at the low level, yes, in order to generate the binary that actually gets loaded onto an NVIDIA GPU, that's only NVIDIA is doing that. But to go from the high-level language to this sort of assembly description of what should be happening, that is being done by a lot of different software already.
Yeah, but at the moment, as far as I understand this, for STD PAR, you need NVC++.
That's right. You know, but that's because it isn't necessarily a well-accepted standard at this point. Mm-hmm. But if you look at SYCL, for instance, LLVM, you have an open source compiler, can now target Intel, AMD, and NVIDIA hardware, right? And once there is a standard for these things, for sure, there will be open source versions, you know, GCC and Clang and whatever, there will be versions of it. Of that, I have absolutely no doubt.
Okay. Maybe for the sake of dinner.
Yeah, really. And we're already, what, like 50 minutes in, and I'm only about halfway through. Maybe I'll just run through some of these things very quickly. Event generators. So let me quickly summarize what we do with event generators. We had two main thrusts with event generators. The first was, so we were working very closely with various teams at CERN who are developing these things. The first was with the leading order matrix elements integrator from Sherpa, which was once called BlockGen and is now called Pepper. And so there was a version that was developed from the ground up for GPUs. And the CERN team has been developing the CUDA version, and we did a Cocos version. And from these plots on the right, you can see the GPU runs about a couple orders of magnitude faster than the single-threaded CPU version. So we see some, very, very good performance there. And by porting it to Cocos, we were able to run basically on all the different sorts of available hardware with very good results. For MadGraph, we were again working with the various CERN teams, and there they've been rewriting the Fortran algorithm GPU port in CUDA, and we created a Cocos and a SYCL version of that. and have run it once again on numerous different architectures, and we see some very, very good performance and very good scaling as well. For instance, on this the graph on the top right, the top line is basically running it on Sunspot, which is the it's a small prototype of Aurora basically. So it's running Intel GPUs with Ponte Vecchio hardware, and we see very nice scaling as we increase the number of nodes and threads. So, of course, all of this has been very, leading order. And frankly, who cares about leading order, right? It's important, it's a first step, but it's only a first step. And the next question, the big question is, what do we do next? And so we would really like to be able to move beyond leading order to more complex things. And unfortunately, there's a number of challenges with this. Some of them are technical. A lot of these NLO libraries require quad precision, which does not work well on GPUs. GPUs are going in the other direction. They want, half precision and less. And also NLO algorithms are very divergent, so they're not GPU friendly at all. So there's really some challenges running on GPUs. There's also some political challenges as well. A lot of the loop libraries are developed by non-DOE and non-US collaborations. So as for CCE, that becomes more complicated. There is a newly awarded SIDAC proposal, which includes porting only the NLO codes and MCFM, where the developer is US based, so we could get involved in that. Some options moving forward are working with MadGraph, or discussing porting some of the for loop libraries that MadGraph is compatible with, and also complementary to the MCFM port, be making a GPU version of Pythia for showering. Let me quickly also go through some of the complex workflows issues. So our workflows, HEP workflows in general, are very monolithic. They're very custom. And they serve very specific use cases, and they do not map well onto HPCs. Being able to use our workflows on HPCs in a more transparent way, I think, is a very, very important step. And especially as we start making greater use of HPC facilities. In the past, we've tended to use them for very specific purposes, like event generation or very specific types of simulation, where you have very simply coded workflows. If we want to make better use of those, or more use of the facilities with a wider range of workflows, we're really going to have to work on integrating the way we shape our workflows for these HPCs. And right now we have this opportunity to harmonize, experiment agnostic components and tools to look at things like, task graphs and monitoring and resource allocation and resource monitoring. And so what the HEP CCE workflows group has been doing is actually to look at some of these different experiments, like DESC and LSST, and seeing how their workflows could be instrumented. So for instance, looking at interoperability between various workflow systems, like FuncX and Parcel, looking for common task graph representations, and being able to streamline remote execution, and being able to really understand what is happening at each of the levels of different task graphs, and be able to monitor it and properly. Alice has been looking at FuncX for some workflows. With Ruben and DESC, we have been looking at Parcel and WorkQ, and we've been able to see some very good commonalities, and hopefully we'll be able to make use of these things in the future. So HEP CCE in theory ends in 2023. We still have a lot of work left to do this year. We want to basically finish up all of the remaining ends that we haven't tied off yet, and we want to come back to the experiments and present our results. We need to make a bunch of white papers to actually go through these things in greater detail. But we're also looking at the future and what can we do in the next, say, 5 years. And so we've come up with a bunch of ideas for various things that we could look at. And so here I'm just going to go quickly through some ideas and proposals. And we're really looking for a lot of community feedback and community input for things of what does the HEP community in general see as desirable avenues to explore. So we've looked at PPS, and I think we want to go we want to continue looking at PPS and apply the lessons that we have learned there, working with the experiments to try to apply some of the lessons learned, looking at things like, codes and libraries, data structures, experiment sizes, and seeing how we can make good recommendations back to them. We want to be able to develop experiment agnostic examples and algorithms, maybe like cookbooks, saying, if what you're doing looks like this, then you want to do that, and you definitely don't do this. And we want to make some training examples so different experiments can actually explore some of these different portability layers. We really want to develop some prepackaged mini apps for the Ask Your Facility testings. This is, I think, is very important for us to integrate with them to be able to say, look, here is a representative workflow. Here's a representative test bed for us. This is what tracking looks like when we run it on a GPU. Here is a Docker container, run it, and let's see how it runs on your next generation platform. We want to be able to have, as the hardware and as the software evolves, we want to be able to benchmark the performance of our mini apps and our representative apps to be able to help the HPCs and also the funding agencies direct the next generation of the facilities. And we really want to continue monitoring the hardware. When I showed that picture of what the landscape looked like in 2019, if we said, okay, we're just going to look at this and we're going to make recommendations based on that, then I have a very, very different recommendation than what we see now. And things continue to change at a very rapid pace. So we really have to keep on going back to the various test beds that we have looked at so far and see how they change in the next 2, 3, 5 years. The other thing we want to go is from portable application to portable workflows. We see much greater use of HPCs and HTCs in our workflows. And right now, we've really been treating these facilities as one-offs. We rewrite our workflows for a specific analysis facility, and we can't continue to do that. We're wasting too much time doing that. So we need to actually develop tools and services and policies that homogenize and simplify this process, looking at things like identity management, software delivery and container management, computing and storage resource brokering, looking at resource availability and overall throughput, scalable distributed execution engines like Dask and HPX, frameworks as a function like FuncX and Parcel, inference as a service with Sonic and Triton, data cataloging, delivery and access with things like XTruD and Globus, and edge services, pilot submissions to things like Harvester and also remote logging and reporting. And finally, one other avenue that I think is very important to explore is machine language training for HEP. Right now, our machine learning algorithms are anomaly detection, pattern recognition, detector simulation, and a lot of them are not small. They take multiple days to train. They take a lot of memory. Some of them are actually reaching the thresholds of an H or A100 nation with 80 gigabytes. We have the MI300, which just came out yesterday, which is 192 gigabytes. I bet we're going to beat or we're going to meet that threshold relatively quickly. So the future thresholds are going to involve petabytes of training data, terabytes of memory, and thousands of person hours to train. So we need to kind of do the same thing we do with CCE PPS and identify and develop suitable training or scalable training solutions for HEP applications to be able to evaluate performance of these data parallel machine language training components like PyTorch and distributed data parallel, TensorFlow, and look at optimizing tools like Horvath and Raytune. And take all the lessons that we've learned from the whole process of PPS and apply it to the machine language, the machine language and AI world. And maybe I should pause for questions. How are we doing for time? Maybe I should just hand it off to Peter at this point, then we can come back, see if there are any last questions. I don't see any hands raised. So in fact, yeah, why don't we hand off to Peter at this point, and then maybe we can come back.
Okay, Charles, do you want to share the slides from
either
the
me
room,
or
or do
you,
you
as you
want?
wish.
Why don't you share?
Sorry, can I?
That makes it.
All right.
Just a quick question for Charles. Can you send us, my way, the Alpaca developers, etc., the comments you got or received about the usability of Alpaca? Because you mentioned it was one of the difficult to learn. So if you have any concrete examples of what should be improved, I'd be happy to discuss it with them.
All right.
Thanks.
Oh, sorry, we do have one hand up on Zoom. Enrico, do you want to just quickly say anything?
Yeah, just very quickly. I'll be quick. I'm the Pepper developer, just to introduce myself, one of them. Actually, we are working from Göttingen in Germany and from Fermilab, so not from CERN. But my actually comment is on the statement that leading order is not that relevant. And I would challenge that a little bit because the way we do our standard, like the heavy hitter sample production at Atlas, for example, with Sherpa, higher multiplicities are merged into the samples at leading order, and they actually cost a lot of computing time. So this can be actually 50% or more of the overall computing time spent. So leading order matrix element at intermediate or higher multiplicities can actually also be relevant. But of course, NLO will also be the next thing. That's true.
I'm very happy that you said that, because one of the comments, I mean, a lot of this material was presented at CHEP, and a number of the comments were, well, this is just LO, we want NLO, but it's very good to hear that people actually see the value of leading order as well as NLO.
Yeah, I can only speak about the Sherpa usage at Atlas and CMS, but for that, it's definitely the case, because we, for example, simulate up to 5 jets at leading order, and we only simulate up to 2 jets at next to leading order. And the efficiencies get very, very low at high multiplicities. So we actually spend a lot of cycles waiting for accepted events at these higher multiplicities at leading order. And that's why a lot of time is spent there.
Great, thanks. All right, Peter, go ahead.
Yeah, okay, thank you. Thank you for inviting me to present the results and plans for HEP CCE iOS. I extended the pool a little bit and added Amit and Ray to the mix because they really did most of the work and they can report much better on it than I can. So we will switch through speakers during the presentation. Next slide, please. Okay, so input, output, and yes, I can see it now. Input, output, and storage. Our activities, we really have 3 major thrusts within iOS for the current cycle of CCE. One is to measure performance of root I/O. Most app experiments, of course, use root I/O on HPC systems. And there's a tool, Gaussian is a scalable HPC I/O characterization tool that we enhanced and used to measure HEP production workflows. Ray will tell us a little bit more about that in detail. The other thrust is to investigate HDF5 as an intermediate event storage for HPC processing. So the plan was never to replace root as our main storage software for our data, but to investigate whether workflows which are operating on HPCs, whether they could benefit from having their intermediate data stored in HDF5, which is more HPC native. Because it's intermediate data, we would still, we planned on relying on root serialization to serialize our very complex event data model used in simulation and reconstruction. We looked into HDF5 features such as collective writing to avoid things like merge steps that can become serial bottleneck. And during testing, we relied on our mimicking framework to understand scalability and performance of our workflows well beyond what we are currently accessing in our production workflows. Lastly, and a little bit later than the previous 2 thrusts, we investigated together with the PPS folks actually HPC-friendly data models. We have heard that for offloading to Accelerator, data models need to be rethought. And that is similarly true for storage on an HPC. If you want to store data more natively in formats such as HDF5, you don't want data models to be too complex. And we are starting to look into making our data models more HPC friendly. So that gets us into details for the thrust. Can we go to the next slide? Yes. And that's I/O and storage on HPC. And here I hand it over to Amit. Amit, take it away.
Thanks, Peter. So there are significant differences in the STCs and SPC resources, which makes it harder to move our framework into the SPCs and fully utilize their computing power. So this is especially true for SPCs that heavily rely on general purpose GPUs to accelerate the compute task, for example. So the HEP CCE iOS group studies the I/O and storage of the HEP general computing framework in the HPCs. Some of the challenges that needs to be addressed for this are storage challenges, since we need to write our data in the HPC friendly format. This usually means the storage format that supports parallel file systems. Second challenge is the I/O, since the I/O of the current HEP computing frameworks are optimized for STCs, and we want to find ways to implement parallel I/O with minimal changes to the existing workflow. Based on the EDM workflow and available compute resources, parameters like compression, chunking, level of parallelism, and multi-threading needs to be tuned. And data mapping is mostly a balance between I/O performance and storage size, and we need to also look at that. So in order to look at all these aspects, we have been developing a test framework that is experiment agnostic, supports parallel I/O using MPI and SDF5 libraries. It supports multi-threading using TBB libraries, and it allows users to do the tuning of I/O parameters for optimizing performance and storage. Next slide, please. Okay, so since HPCs rely on parallel file systems for their performance, the HEP data should be stored in the format that can utilize these file systems. HPCs have a fairly established I/O software stack that is used to support parallel file systems. When we say HPC friendly storage formats, so they are basically like SDF5, for example, provide high-level libraries that can hook into these software stacks and allow us to take advantages of optimizations like collective I/O, where multiple parallel processes perform I/O on a single file and hence bypass the need to merge different files that would otherwise be created by different processes, for example. Next slide, please. So now most of the HEP experiments rely on root framework for their computing and storage tasks. And HEP data models are usually optimized to work with root, and root has evolved to fulfill the HEP requirements. This has allowed the HEP data models to be complex enough to support C++ language like pointers, inheritance, polymorphism, and so on. Root usually stores this complex data in T-trees, and we use all these internal libraries. But the thing is, the root works best in STCs, in which we rely on and may not be well suited for the HPC environment. So let's go to the next slide. So in the HPCs, like I said, other storage formats like SDF5 can work well, but they will have different data model. For example, in the case of SDF5, data is written in S5 datasets along with the attributes. And then we can organize these datasets into groups and stored in the file. SDF5 supports parallel I/O using MPI libraries, which can simply be turned on by turning on some MPI flags. Next slide, please. Okay, so in order to use the HPC resources, we need to find a way to write our data which are complex C++ objects in HPC-friendly storage like SDF5. One thing I want to point out is that the design of the data products is experiment-specific, but the common thing is that they are all supported by root. So we use the test framework uses root as a common tool to serialize this C++ objects into byte stream that are supported by SDF5. And the byte stream data can be mapped is shown in the slide. Data in this example, data products X and Y are serialized using root before writing them into a single SDF5 file. This is one way of mapping the data so that different data products can be written into a single SDF5 dataset with one additional dataset. There are other ways to map the data as well, and our choice of mapping depends on our requirement to save on IO versus storage, for example. Next slide, please. So here we saw the IO performance in terms of event throughput we did in NORS. Basically, in this, on the left plot, you can see the throughput as a function of the number of concurrent events. The yellow is 4 parallel processes in one compute node. The event throughput with 32 threads can be achieved with 64 threads divided among 4 MPI ranks per node. So this is basically what the left plot is showing. So if we take this study and scale it to multiple nodes with different level of parallelisms per node, we can see the performance on the right. Here we see that the performance improve as we increase the ranks per node, but start to saturate going from 1 to 2 to 4 per node, for example. Obviously, which setting works best depends upon factors like CPU architecture, event size, and type of compute task. And if we look at how much the application spends, how much time the application spends during the runtime, we can see that external MPI calls implemented takes 14%, writing data into SDF5 takes 32%, and others take 54%. Okay. I will now hand this to Ray for Darshan.
Thank you, Amit. Yeah, so Ray is next, and we will hear some details about the Darshan thrust.
Okay, thank you. Thanks, Peter and Amit. So I will go into a bit more details about Darshan and what we have used Darshan for. So as Peter mentioned, Darshan is a tool that we use for IO characterization. It is very lightweighted and capture cross view and entail traces of applications IO behavior. Darshan right now is widely available on many HPC facilities, including LCFs at different labs, NERSC, and also it's in the CVMFS. It has become a very popular tool for HPC users to better understand their IO workloads. It's very easy to use, so there's no need to change anything in your code, and it's modular. So any new instrumentation sources can be added to the Darshan library in a very straightforward way. Next slide. So Darshan originally was designed specifically for MPI applications, but recently we, including the Darshan experts, have modified it to be also work with non-MPI contexts. That is because HEP or workflows are traditionally not MPI based. So if you check out any Darshan version that's above 3.2 and so if you check out any Darshan versions that's about 3.1, so that non-MPI can be instrumented. And also in a recent release at 3.2, that Darshan is also adds the ability to instrument the dynamic linked executable. So Darshan also have added the ability to instrument the forked process that is very helpful to instrument the multi-process Athena MP. So as we know that Athena MP is using fork to create those parallel workers from the main process, as shown in this schema view here. So with this ability of instrument the forked process, we can looking at the IO behavior of each of those worker process. And here you can see an example on the right. That is a heat map of the data access of each of those thing and forked process of a single Athena MP job. So there's details of the data access of read and write on each of in each of the time intervals shown here, including on the top the profile and on the right for the time interval and each of those process. So next slide. So we have made case studies on Atlas CMS and Dune workflow. So here I'm just showing the two examples from Atlas and the CMS. We studied the different stages of the Atlas and the CMS workflows on different machines at Argonne, BNL, and NERSC. So here this is showing what we have taken a look into as an example on the I/O operations. So we compare most the I/O operations in all the stages we have studied, and one thing we notice in the workflow is for most of them, we get this equal number of reads and seeks. As you can see here, as example in the CMS reconstruction, the plot that's being automatically produced by Dashin, that there's a same number of writes and seeks that's showing here. And this is similar for all the stages that's been marked here. Also, for those I/O operations, they are equally sequential or conservative I/Os. So you can see an example that's hacked on the shared writer process in the Atlas Athena MP job that the I/O pattern plots that's been showing on the top right. So next slide. The only few exceptions that we see a different behavior on the I/O and on the I/Os are the filtering stage. Well, there's much more seeks and reads that we found during the filtering. That's the same behavior we saw on both Atlas and the CMS. So in the Atlas worker process and the CMS filtering stage, there are about twice of them, 6 compared to the reads, and more of those I/Os are sequential compared to conservative. Next slide. The other example is the access serve size. So here we show 2 examples of Atlas CMS both on the simulation stage. You can see that most of the read and writes are very small here. So they are at the order of around 1K for both 2 experiments. The only exception that we saw across all the stages that we have looked at is the analysis stage at Atlas. So here you can see the plots provided by Dashin that there is majorly larger reads of order of 100 kilobytes. So we have looked into these small reads and writes, and the current thought is this is related to the root T2 cache vector IO support in uncertain file systems. It could be a potential bottleneck of the workflow. One thing that could be taken advantage of is the already existing data saving concept in the root. Okay, I will give it back to Peter for the next slide.
Yes, thank you. Next slide, please. I think you can see the slide change in the video, but on my screen it hasn't changed yet. So we have a couple of recommendations that comes for iOS as well. So I think the work of the HEP CCE iOS team has resulted in worthwhile insight into the I/O behavior of HEP workflows, including on HPC and at scales which are beyond current production, partly enabled by our I/O mimicking framework. We have had fixes and enhancement to common software and experiment frameworks. Also to tools which were provided, including Darshan. So as Ray pointed out, we added fork safety to Darshan, not only helping us to use Darshan, but also making Darshan a more universal tool. We have fixed the root serialization bottleneck which was discovered with our mimicking framework, which otherwise we wouldn't have seen yet in root, but at some point. And we had developed a patch to resolve Athena library issue and a crash that was connected to that. We have done prototype development for new functionality in collaboration with the experiments. As Charles has pointed out earlier, one of the characteristics of HEP CCE is the involvement of experiment experts. Many of us are part HEP experiment and part HEP CCE. And that has been very fruitful. And as one example, Atlas developed the functionality to store our data in HDF5 pretty much using the HEP CCE developed example and plugging it into their software. So that has been very beneficial for us. Next slide, please. Our next steps, that's actually very similar for PPS and iOS v2. iOS 2 is writing reports to be published. We are speaking to our stakeholders and we are presenting to the HEP community right now to HSF. So that's being done to kind of publish and communicate our results and findings. Next slide, please. So I would now switch into the continuing program for HEP CCE iOS, similar to what Charles has. So we heard about the results. And now I would like to discuss the upcoming cycle. And here I too should have had that red box that everything I'm presenting now is still in the planning phase and nothing is final, but it should be discussed in forums like here. Next slide. So I split this a little bit into two sections. One we will hear now is more the continuing work from the current cycle, and there I will have the experts present again. And then later we will add new plans. Amit, do you want to tell us a little bit about the next plans for the data model work?
Yeah, so what I have shown earlier is the development and testing with the framework that takes HEP data products, converts into HPC friendly format using root and writes into HDF5. So, but since HPC relies on things like GPUs to accelerate the computing task, the serialized data products cannot be offloaded into the GPUs directly for computational tasks. So using GPU might require us to develop data models that are simpler, for example. So please go to the next slide. So in the next iteration of CCE, we will be working on developing data models that are HPC friendly and can not only be offloaded, but also stored in the HPC friendly format like HDF5 without having to serialize them. So that's one of the plans. So next slide, please. So as a part of this initiation, we are developing a framework to study and design HPC-friendly formats for the HEP experiments. Future expansion of this project will be based on the effort undertaken by various experiments to make their data model HPC-friendly. So we carried out this survey to know what are the efforts that experiments are doing to make their data model HPC friendly. We invited speakers from various experiments to share their experience of developing their data model to be HPC friendly. So the results are in the hyperlink here. So you can go and see the result. Next slide, please. So this is a screenshot of a summary, and again, the details are in the link below. But what we found was experiments efforts are based on their current data model, which means experiments want to retain as much of their current data model as possible. This makes sense since we want to minimize the changes in our code base. However, they do acknowledge that some of the transformations are necessary, like changing the data that is sort of array of structure to structure of arrays type. So based on what we learned from the survey in the CCE2 cycle, we want to implement the generalized approaches taken by the experiment in the test framework that I mentioned earlier. We want to implement tasks that are simplified and generalized, but sort of mimic what our experiments do that can be offloaded into the GPUs. And the goal will be to ultimately have this test framework also is some kind of training tool, if possible, with these resources that I mentioned above. Thank you. Next slide.
Okay, next slide. And then we are hearing the future plans on Darshan. Wei?
Yes, thank you. For Darshan, I will split into Darshan, the tool itself, and the plans on the experiment characterization side. So on the Darshan developments, there are two major parts. One is on the instrumentation. As Aurora is coming, Darshan will add the support to the Aurora DAOs libraries for their new storage system. Appealing performance characterization for the IO middleware can be effectively leveraged by using this storage model. So that will be released in very short time for the next major release of Darshan. In parallel, Darshan also will deliver more user-friendly analysis tools, especially targeting for the workflows. So this effort have been made to refactor the PyDarshan code that's been developed by the Darshan team to aggregate and virtualize the Darshan data. So after this effort, PyDarshan will be able to easily visualize and aggregates Darshan records according multiple logs. So this is not only including the multiple logs that's been generated at a different stage of the HEP workflow, but also the ones like as mentioned before for the logs that's being generated by each of those children process. So the Dashen team will have several students from various programs that's doing this development during the summer. So next slide. So on the workflow side, and there we will continue on this I/O characterization in the HEP CCE 2. So that's including capture the MPI and HDR5 I/O in the workflows, and also working on the GPU workflow benchmarking. We're also interested to do studies and to see what's to use Dashens to instrument the HEP applications when working inside the containers. So, and with all those monitorings and an analysis of those workflows, we hope to get a better understanding to help to optimize the storage parameters of our data products. Besides the characterization, one thing we would like to delete during the HEP CCE 2 is to have the monitoring functionality of the HEP workflows using Dashen. So that's including the software release monitoring. For example, the plan of stress the spots at Atlas with Dashen, and to integrate the task monitoring with Dashen to be able to have a better monitoring of data access on both input, output, and conditional data, and monitoring them separately for each of those workflow tasks. So next slide, I will give back to Peter.
Thank you, Ray. Thank you, Amit and Ray. So that was an overview of the more continuing activities which we suggest for the next iteration of CCE. In addition, we plan some rather new activity which I would like to present. So the current cycle of HEP CCE has mainly focused on porting HEP workflows onto an HPC to tackle the upcoming CPU challenges. But in addition to the upcoming CPU challenges, we have similar challenges in storage. And I added a plot here from Atlas, which is familiar to many of us, that our storage needs for high luminosity LHC are much higher than what our budget can buy. So we plan for adding a new section, which we call storage reduction strategies or so. Can we go to the next slide? So, as I said, so currently we have mainly looked into HPC, porting to a HPC that addresses the CPU cycles needs, but has very little or only secondary effect to disk and tape storage crisis. So we need to address that as well. Next slide. So there are a couple of directions we have, and the first one is maybe a very obvious one, but here I found myself in a tough spot because this meeting is in addition to the Atlas core meeting we just had, where we had discussed Route 7 migration and in particular our N-tuple. So I find myself in the tough position to either repeat what we have discussed there or to leave this very brief, probably briefer than it should be, but I decided on the second one, and given the time, that's probably a good decision. Our N-tuple will be part of Route 7. It has been implemented in both Atlas and CMS for their most derived production analysis data. From there, it promises significant storage savings and I/O speed up. And storage savings, of course, is what we would like to address. We have seen things like 20–30% of storage reduction. That is a big step towards solving the storage crisis we have for high luminosity LHC. However, our N-tuple also comes with limited data model support versus root T3. That's because of a streamlined design of our N-tuple, and that requires a leaner approach than T3. And we don't really want to not do that. We want to find a fair balance between keeping our N-tuple very streamlined, yet supporting what we really need to support in our data models. And when I say what we really need, I think that means the experiments should revisit their rather complex simulation and reconstruction data models and make adjustments to that. Those were developed at a high point of object-oriented design, and maybe we should make adjustments. And I see a HEP CCE role here in two areas. One is we can develop common techniques to hide the current complexity in those data models from the persistence, from our N-tuple, but also from HDF5. And that work is synergetic to our earlier work of the HPC-friendly data model, which Amit has presented. And on the other hand, we can do performance testing on optimization of those techniques, and there we can use things like the Darshan monitoring tool we heard about from Ray, or the I/O mimicking tool, which was developed as part of the iOS group. Then the second part where I think HEP CCE can play a good role in our N-tuple development is to consolidate requests from the experiments for additional functionality to root. So if experiments need larger support for certain features of their data models, then maybe consolidated requests to the root team would be better than having conflicting requests from Atlas and CMS and Dune. Okay, next slide, please. Another avenue of saving storage space is lossy compression. All experiments now in root use lossless compression. That's an old hat. We have done that for decades. And there's even some lossy compression we use on our most derived data. CMS does do some float compression on their nano AOD, and hopefully soon Atlas is doing something similar on their first light data product, which is targeting run 4. But really advanced and intelligent lossy compression has not yet been used widely in HEP. And we have had a few talks, which I list here, about intelligent data compression methods, which are used in other areas of science, and which promise storage reductions of a factor 10 or even 100. Now, I'm not advertising that we could use that on a data product and make our first light a factor 10 smaller, but there may be areas within our data models where we could benefit from these more advanced compression techniques, and we should work with these experts, computational science experts, to see whether we can implement some intelligent compression within parts of our data model. So I think those are the, next slide, please. Those are plans for our future activity, and closing out now, thanking you and thanking the whole HEP CCE crowd for their work, and you for hearing us here. Thank you.
Thank you, Peter. Let's take some questions both for this part and also for anything that came up to it. Anybody on Zoom?
Yep. So thanks for the nice talk. This is probably a very naive question, but I was a bit puzzled maybe about this HDF5 business, because I'm not completely clear in my mind how much difference there is between, say, a flat root and tuple, not one that's full of serialized, but and an HDF file in terms of how it's handled in an HPC. What actually is it about HDF5 that means it works better with HPC than a flat T tree or maybe RN tuple in the future? This is maybe because I'm assuming that all this conversion to HDF5 from whatever formats are ingested must take quite some resources as well, right? All this translation of.
So maybe I can answer that, and then Amit can correct me when I get things wrong. So it's not really a conversion. It's for intermediate data products. So it's for data products which we write out on an HPC and then reread on the HPC to do as a next step. So there's no conversion, but it is persistifying complex data. For example, reconstructed data model, not analysis and tuple also. One of the advantages, and Amit, I thought showed that, is that we can easily implement things like collective writing, so that we don't have to do any merging step or have to deal with very small files such as we do in Atlas, event streaming, event service. But we can collectively write to one larger file. So HDF5 has advantages that it is more native to HPCs. Therefore, you could expect better support on their parallel storage infrastructure. The other advantage is that it allows you easily to collective write via multiple nodes, collect output from jobs running on multiple nodes. So in some sense, we expected to have better HDF5 support for highly distributed job or highly parallel jobs. But again, it's not meant to be a final data. This was really just for intermediate data products. We are not suggesting, or we did not study replacing a final data product with HDF5.
Just maybe a comment, Peter. This phrasing of how native it is to HPCs, I think this is sort of ticking a couple of us off. That, well, no, so HDF5 is a widely used thing. It absolutely is a very widely used and very widely supported thing. But saying that, well, it's just more HPC than other stuff. The point that you made are good points, but by itself, this statement is sort of weightless.
So let me just point out that when new machines come on, such as Aurora, that many of the early science projects include HDF5 libraries, whereas root is less popular. Now, I'm obviously not arguing against root, but the point here is that sometimes HDF5, you can get more expertise from the high performance computing side than in root. That has been a challenge in the past to fully include computational science expertise if you talk about root persistence, and that's not the case with HDF5.
Anybody else? I see.
Little follow up on this one. I just want to add that just to strengthen what Peter is saying, that certainly no one is arguing that we should replace root with HDF5, but there are experiments which are stakeholders in FCC who are planning to use HDF5 for the raw data, for example. So it's something that should be on our map, even though most likely won't be used by LIFC experiments.
Yes. Now, thank you, Paolo. That's a good point. Now that's something we will pay more attention to in the second cycle. So this cycle was really the intermediate data product via root serialization. In the next cycle, we will maybe pay a little bit more attention also to whether we can use HDF5 as a genuine data product. For example, Proto-Dune is currently putting their raw data in HDF5. They're thinking about some analysis products in HDF5. I'm not advocating to store analysis data in HDF5, but I advocate for the functionality that if there is a client who wants to have data stored in HDF5, then maybe developing common functionality is helpful.
Maybe as just a question from my side. So HDF5 is very popular indeed. Did you guys consider or even look at some other popular products from industry, like Parquet, Arrow, sort of things?
Yes. So at this point, no. However, I think by being able to look at the first alternate, and I think that's another advantage of looking at the different format, even if you don't want to necessarily use it. By looking at the first alternate candidate, you kind of make the developments it would take to write to Parquet or Arrow, you make them much easier. You find concepts and to abstract your I/O. And because it has not been our goal to replace a data product into a different format, we haven't really looked into these things, but I think we have put in infrastructure that makes those studies easier. Does that make sense at all?
Sure, sure.
Yeah. And in particular, I have to point out maybe our I/O mimicking framework, where you can rather easily provide these backends and then, you know, just add another Parquet writer and reader, and then you can test writing experiment data to Parquet and see the performance
there. And again, to jump in, if the experiments think that we should look into Parquet because it's useful as a sort of a risk mitigation alternative technology, we would love to get this. We'd love to get this feedback from HSF and from the experiment, from anyone. I mean, at this point, we are asking for input on a sort of very generic plan.
So did people from Alice give you feedback? Because I thought they were in this business on this data format. But at the same time, my own knowledge is sort of limited in this area.
I'm not aware of any feedback from Alice.
Yeah, me neither. I was waiting for Paulo to say that. I haven't heard back from Alice. Now I have heard the suggestion of looking into Parquet before, Attila. You're not the first one to bring that up, and that may be interesting. And as I said, I think we have put into place many tools that would make such a study easier.
Okay, well, I leave it to you and Ben to.
I don't see any more hands, so I'll leave it to Ben.
Yes, well, thank you very much to both to Charles and Attila for chairing today. Again, apologies that I couldn't be there in person, but unfortunately, UK flights were rather disrupted over the weekend. So with that said, thank you again to Charles, Peter, and the other speakers for a very interesting talk, and also to everyone for attending and some very interesting discussion as well. So we look forward in the future to hearing more from CCE and the work that's going on there. So with that, I will now close the meeting and stop the recording. Thank everyone again, and obviously hope to see you at the next meeting in July, where we'll hear about Alice 02. So thanks everyone. Have a good evening or rest of the day, and see you at the next Compute Accelerator Forum. Bye for now.
Thank you. Bye bye.
Bye bye.
Bye.